Hello everyone, I'm the speaker Bill, and today I will introduce the sea level anomalies affect the abyssal current. First, let's speak about the abyssal current. What is abyssal current? A current means a temperature below 2 Celsius and with high density and with a deep depth. If you feel this status, you are an abyssal current. So which means there's many abyssal current in the world. And our main current today is AABW, Antarctic bottom water. And let's talking about the importance of AABW. It's a major component of the thermal highline circulation. And you can see, as its name, Antarctic, it transports water from Antarctic and go to the South America and goes straight to the Atlantic Ocean and be a part of thermal highline circulation, which means it may be affect global climate. Thermal highline circulation is just look like this and transfer from Atlantic Ocean to the Antarctic Ocean to Atlantic Ocean. Look like this with this route. And recently, we found that there's an anomaly in the AABW current. Its temperature increased and with a velocity drop. And what's happened? A blocking event. So the purpose of our study. There's two purposes of our study. We explain the changes in the deep ocean are connected to the sea level change observed. And the second our purpose is open a discussion of the importance of the air-sea interaction on the water exchange between deep ocean. So we still have two hypotheses. The first, variability in abyssal current is linked to CSLA, and change in deep ocean circulation may affect the global climate. Let's see this picture. There's two pictures, and just see the left one. The green diamond is the place we put our velocity sensor, LADCP. And there's a black block here, is a VEMA channel. It's a place where the AABW acts. And this picture shows the potential temperature of the AABW surroundings with a depth over 3,800. And there's a big black area here below the VEMA channel. It's the entrance of VEMA channel. And let's see the right picture. This shows the velocity of AABW. And from a sulfur altitude, there's a slower velocity here. And it comes from the entrance of the velocity, look like here. And it goes to the VEMA channel, then you can see it speed up, accelerating, because it enter the VEMA channel and go to a narrow space and make it accelerating. This picture shows our LADCT data in the VEMA channel, and the space look like here. This channel is the VEMA channel. And there's a blue diamond and green diamond here. This is our LADCP sensors. And if we put the green diamond here into a graphic, shows the velocity. And there's a below picture shows with the x-axis with the time series and the y-axis with the velocity. We can see it change with time. And we use a blue bar shows here. You can see at the first time, there's many velocity with a high speed are above the blue bar. And a few years later, most of the time, the velocity is below the blue bar. So we can see there's a drop of the velocity. And this is the anomaly we mentioned above. So now we will explain this. The variability in abyssal current is linked to SLA. This picture shows the correlationship between the SLA and bottom velocity. We can see there's a red-black area. What does that mean? It means there's a strong correlation area in the entrance of VEMA channel. And from the vena channel, it transports water to the vena channel. And because this water is affected by sea level anomalies, so transport from here, any water transport from here, affect the vena channel current, and that is AABW. And what happens if the AABW current velocity is changed? We call it blocking event. What is blocking event? It's the current with the velocity does not exceed 10 centimeters per second. We can see there's a picture left with a time series for x-axis and y-axis for velocity. A, B, C, D, E. It means the different time series of this current and with the same place. And there's 8 blocking event during this time series with a great blocking here. There's 8 blocking event. And let's link this velocity with the sea level anomalies we mentioned. Let's see the first picture here. The above picture is the velocity we showed in the last page. And here, the 8 pictures. We see this blue areas, and we call it the negative sea level anomaly. And let's see the velocity in the AABW, which means vena channel here. We only have 2.4 centimeter per second, which is really small. And let's see B pictures. There's a big red area, and we call it the positive sea level anomaly. And the velocity in the vena channel is 40.3 centimeter per second. It's really fast. So we can get a conclusion. The positive sea level anomaly makes AABW faster, and if this is a negative sea level anomaly, which is the blue part here, it makes the AABW slower. And let's go to the take-home message. It's really easy, and we can explain everything we mentioned with just these pictures. Please follow the red star here, and let's see the red word here. We can see there's a sea level anomaly with a red color. It affects the head pressure here in the entrance of vena channel. And if there's a head pressure in the vena channel, it means a higher pressure gradient between the entrance of vena channel and vena channels. What that means? Increase the velocity of the AABW. And on the other hand, if there's a negative sea level anomaly, it means there's a lower pressure gradient here, and makes the AABW deceleration. So we proved that the first hypothesis is true. The variability in abyssal current is linked to sea level anomaly. And this is our second hypothesis. Change in deep ocean circulation may influence how the ocean responds to rising sea levels, affecting the global climate. But in this hypothesis, we have to say we don't have enough data to prove this. And that is why our purpose of this study, the second one, is open a discussion of the importance of ALC interaction on the water exchange between deep ocean. The deep ocean means our abyssal current. We want more people can conduct more research here after this speech. So this is our second purpose. And if we can get more data, we can prove our second hypothesis. This change may really affect the global climate. And this is our method. We use the satellite to see the sea level anomalies, and we use the correlation analysis to see the correlation between the velocity and sea level anomaly. Then we use the LADCP to see the velocity, in situ velocity here in the vena channel. Then this is our reference. Thank you for listening.
Hi, sorry, can I ask what the green diamond meaning in some of your picture in vena channel?
Green
can
diamond.
you explain again? Yeah,
Here. Oh, this is
no, in a deep picture.
Oh, this one. Right.
Yeah.
Oh, The blue diamond and green diamond also, they are both means the LADCP sensor. But the green one, we just show the velocity of the green one in the bottom picture. And that's the difference. And if you mean the pictures here, the green diamond is the place in the VENA channel, the center of the VENA channel. And this is the place we put our LADCP sensor.
Oh, so the green point is more important. We need to attention.
Yeah, green diamond is the most important part in this picture.
Okay, thank you.
Sir, may I ask you what caused the sea surface anomaly? Because there is a picture that presents the velocity number there is a big difference for 3 centimeters per second and 40 centimeters per second.
Okay, at least I would say I delete all of the reason why what caused the sea level anomaly is because this is not the most important thing of this research, but it mentioned it because of the anticyclone and the cyclone here, but it's not really strong here, but it still affects the deep ocean. It didn't mention many data about the cyclone and anticyclone, but it just say what makes these sea level anomalies happen.
Okay.
Could you go to introduction of abyss currents? Do we have any accuracy number of depth or density to be a standard? Like how many deeper land?
I see.
Yeah.
It didn't mention it, sorry. It just mentioned the temperature definition is below 2 Celsius.
Okay, thank you.
I want to know why do we need to study the velocity of the sea level anomalies?
Is that mean why sea level anomaly is linked to velocity, not
Yes.
other? Oh,
Yes.
okay. As we said about there's a temperature increase and blocking event is related to velocity, so let's ignore it. The temperature increase just mentioned it, and it didn't say the relationship between sea level anomaly, so I don't explain it. But the velocity related to sea level anomaly, that's our research done by the sensors, because as we say, the purpose of our study is to open a discussion of the importance of air-sea interaction. What does that mean? It means we lack of data. There's no data about the abyssal current. There's no models and many velocity here, so we can relate more factor with the sea level anomaly or other factor. And so here we just use the most common data, the satellite to see the sea level anomaly and the LADCP to see the velocity. So we can get more data about like salinity or like there's nutrient salinity and others like that. So that's why we use velocity and the sea level anomaly. And is that the answer you want?
Can you explain again the blocking event in 16 page 16? Yes.
Okay. The blocking event is the time series when the abyssal current velocity does not exceed 10 centimeters per second. And that's the definition. This definition is we make it. It's not the common definition I made by other organization or something. And why we say 10 centimeters per second? Because compared to the normal speed, maybe it's 50 centimeters per second. 10 centimeters per second is really slow. And if the abyssal current, ABW current slow down, that means the thermohaline circulation will get less water from the Antarctic. And that may affect the global climate. And that's what we want to see.
Okay, thank you.
This topic is to me, is very interesting. And I think Bill did a good job, but still there's space for improvement. For example, I think Rita's question was a little bit like, why should we care about the whole thing? A little bit like that, okay? Although the way it is phrased is a bit weird, but she was asking, why should we care? And I think you added a very important slide where you talk about thermal highline circulation, right? And I think, although I'm sure in this class, everyone has heard about thermal highline circulation, but maybe you would like to say a little bit more how this influence maybe the climate, the energy budget of the whole planet. Say a little bit more so that we know, okay, thermal highline circulation is not just a flow, but it also affects the climate, for example. Say something about that. And then another thing about the introduction was also related to the question of, sorry, I forgot the name, about the sea level anomaly. Okay, so you say you prepare something, right? Because your talk was, you still have some time. Okay, so I would say maybe it would be great for you to use one slide to explain a little bit about the sea level anomaly, especially because this is the southern hemisphere. So I think maybe the direction of the cyclone and anticyclone might be different from the northern hemisphere. So maybe you can tell us what kind of anomaly you are talking about. And also for me, I would be interested in knowing, okay, you talk about sea level anomaly. I don't know if you have a slide where you show how, okay, so that's the extent of anomaly is actually very small. Okay, maybe that's something you can emphasize, that a small difference of 20 centimeter is enough to change the the speed of a very deep flow. That's actually amazing because most oceanographers tend to believe that what happened in the upper ocean has nothing to do with the super deep ocean. That's most oceanographers believe. But here it actually tells us that, no, this is not the case. Such a small difference can make a difference in the flow velocity. So that's actually something you can emphasize about the number, okay? And then regarding the content, I think it's actually very nice that you have the hypothesis and you reuse this again and again to always keep us in the same thread. So our mind is not drifting around. So we know that, okay, this is related to hypothesis 1 and related to hypothesis 2. This is very nice. And, but I would like to point out that, because I also checked this paper, I think what was not really correct is this is not LADCP. So this is flow meter, okay. LADCP is the data at the background, okay? It's deployed from the ship. So, so if I were you, I would take the method forward to right after introduction. Okay, and then it would be even good if you can look for some photos of LADCP to give us a better understanding. Oh, what kind of instrument you are talking about? Okay, and then try to repeat SLA whenever possible. I know, but you don't have many abbreviation, but it's always good to do that. You use a very small font, says SLA means what? I know, but I already tell you that audience are easy. They forget things easily. Okay, they forget things 3 slides before.
This is an anomaly. So I didn't put it in the next page here. So yes, really close. But I didn't put it here.
Actually, when you write it, I don't really connect sea level anomaly to SLA. Actually, you know, yeah. So it's always good to repeatedly define your abbreviation to think for the audience, and then you use this expression frequently, increase, decrease, larger, lower. This is good because it's easier to follow with arrows. And then one last thing is, this is too dark over a gray background. This is very dark, so change color. Okay, but I think this talk is very nice, so let's thank Bill.